And I will refresh your memory that let me share my screen with you. The last thing that we talked about was generators. And we were up to the point where we were going to cover the test on radionuclide generators. And that's what we'll do now. And then as soon as we finish that, I worked on something yesterday that I think will be very helpful to you. And that is one of the generators that I did not describe last week was the strontium rubidium generator. And I worked up some information for you. It's only about 8 slides. And in the chat room, I put a little PowerPoint file so that if you would like to download it later, you will be able to do so, and then you'll have exactly the same copy as what I have right here. So I'm going to encourage you now to unmute yourself, and we'd like to take this test orally. So if you know the answer, please just give a shout out. Here's your very first question. When we elute technetium from the Molytech generator, what is the chemical form called?
A.
Choice A, right? Pertechnetate. And a good exam question might be, what is the oxidation number of the technetium in pertechnetate? Anyone know? So if you recall from, sorry, someone said?
1.
Not 4. So if you remember from your chemistry days, oxygens are -2 each. 4 oxygens would therefore be -8. The whole anion is -1. So the charge on the technetium has to be +7. +7 -8 equals -1. That's the highest oxidation number known for technetium. There are also states of +4 and +5 and +3 and others, but that is the highest one, the most highly oxidized form. These other things are just totally not even possible. So there's a little brief explanation of the answer to that question. Second question, the parent-daughter relationship that we talked about last week in the Molytech generator is a classical example of which one of those listed?
C.
Sure.
Transient.
That, of course, would be transient equilibrium. Here's a very lengthy explanation of it, just refreshing your memory that in transient equilibrium, the ratio of the half-life of the parent to the daughter is around 10:1. And we say this is a classical example because the ratio is 11:1, 67 hours divided by 6 hours. Perfect example. Number 3, and I'm going to give you a moment to read through these. This is a right off an old exam. I think none of the above was not one of the choices, but the rest of it was. So take a moment to read it, and then you can tell me which one of those is correct for transient equilibrium. Anyone?
E as in dog.
That is exactly the correct answer. The apparent half-life of the daughter. That means that the daughter appears to have a half-life equal to the physical half-life of the parent. We know it doesn't, but in the equilibrium mixture, it appears to. And the reason is that the daughter can't decay until it's formed, and it's being formed very slowly because the half-life of the parent has got to be much longer than that of the daughter. It could be 10 times as much, or it could be 10,000 times as much. So choice D is totally correct. And there's a brief explanation of that. In the Molytech generator, how do we separate the daughter from the parent? And then we leave the parent behind to regenerate more daughter. What is the process called?
D.
D.
D like David?
Yes.
Correct. We use a chromatography column. I showed you a sketch of it last week, chromatography column. These others are just totally incorrect. So it's going to be column chromatography. And the column, if you'll recall, contains Al2O3, that's aluminum oxide. And the reason that it works is there's such a very high affinity for the sodium molybdate by aluminum oxide, but basically zero affinity between pertechnetate and the aluminum oxide. So it's a very efficient way to separate the daughter from the parent. Okay, what is in that chromatography column? It's a finely divided white powder. Which one?
C, aluminum oxide.
Sure, aluminum oxide or alumina. That's the common name for it. Number 6, what do we elute with? What solution do we remove the pertechnetate with?
C.
C.
That would be C, physiological saline, which is by definition, excuse me, by definition, 0.9% sodium chloride. So that would be choice C. Now, we did not cover this last time, and we will do so in a subsequent lecture, but still, this is something you should know already. When we elute the generator, we perform quality control on that eluate. Which list is correct for the tests that we perform on the eluate?
C.
C.
C. Now, here's why you should know C right away. Freetech is pertechnetate. That is what you expect to come off of the column. So that's not an impurity. Freetech is what you want. And so A, B, and D can't possibly be correct. And this one has perchlorate, has nothing whatsoever to do with it. So if we choose to, we can test for aluminum ion breakthrough, but it's no longer mandatory. We must check for moly breakthrough to make sure we're not injecting too much molybdenum into patients. And finally, hydrolyzed reduced, we should test for it. In my department, we've always tested for it, but some people don't. But we're looking for a colloidal impurity that will make every drug that we make go to the liver and spleen aside from the desired location. So choice C is correct. There's a very lengthy explanation for your review at exam time. After a Molytech generator is eluted, how long does it take for the ingrowing technetium to peak, to reach a maximum?
D.
D like David. So what's the actual correct number?
23 hours?
Good, 23 hours. So here's an example where you have to know that number, but that number is actually not in the possible answers, but the only possibility here is 12 to 24, but you're correct, 23 hours. Okay. In transient equilibrium, it's possible for the activity of the daughter to exceed the activity of the parent by how much? So I mentioned last week that in some cases where the half-lives are fairly close to each other, you can actually get about 5% higher daughter activity than that of the parent. We don't see it commonly, but it certainly can occur, and you should know it's about 5%. Okay, technetium, as you know, technetium metastable decays to the ground state. And the half-life of that ground state is 220,000 years. Why does that ground state not contribute to our absorbed radiation dose? Give you a moment to look through the possibilities.
Is it B?
This again, choice D. Let's go down the list. This says the technetium ground state does not emit particulate radiation. That's totally false. It's a beta minus emitter. It's rapidly clear from the body. That's a totally invalid statement for so many reasons, one of which is that until you know what the chemical form is, you don't know whether it's going to clear or stay there forever. So choice D is the correct answer. Here's something that I think we looked at last time, but the decay constant for the ground state is roughly 3 millionths per year. If you compare that to technetium, it's 11.5% per hour for the ground state. So we're not too worried about the decay rate of the ground state, because it's not going, a person's lifetime, it's not going to confer enough radiation to even affect our background very much. Okay, which two of the following are essential for a practical radionuclide generator? That means one that we can use day after day after day. Okay, let's go down the list and you can tell me true or false. The daughter must have a longer half-life than the parent.
False.
False. The daughter must have a shorter half-life. That has to be true. The daughter half-life must not be greater than 1 hour.
False.
False. Technetium is 6 hours. The parent must not decay to daughter by IT.
False.
True.
True.
No, that is true. If the parent decayed to the daughter by isomeric transition, how could you separate them? Is there any way to separate technetium ground state from metastable state? Absolutely not. And I can see why that might be a little confusing question, but think about our generator. The parent is molybdenum, the daughter is technetium. They're not even the same element, so they're easily separable. So the parent must not decay by IT. That is true. The parent must not decay by isobaric transition. You'll recall isobars have a constant A number, a constant mass number. And so what do we have? We have molybdenum 99 decaying to technetium 99M. The mass number is the same. That is an isobaric transition. So the correct answers would be B and D only. And there's your explanation of that. Okay. What helps to affect the separation of the technetium from the molybdenum? Who's got it?
E.
Choice C. Molybdenate is very tightly bound to aluminum oxide. And pertechnetate is not bound at all. Remember, it's the difference in the affinity. Okay, good. You should not get this question on your exam because the aluminum ion breakthrough test is no longer mandatory. Just in case the people who make up the test are not aware of that fact, I've put it in here anyway. What is the legal limit for aluminum ion breakthrough? And the answer is choice E, 10 micrograms per milliliter. That also is the same as 10 parts per million. But again, that test is not mandatory. Okay, what equipment can we use to determine the radionuclide impurities? Think moly in technetium, not radiochemical, but radionuclide impurities. There are two correct answers.
Choice E.
So how do we do the moly breakthrough test? We do it with a dose calibrator. How could we do it? We could use a very high resolution device called a multi-channel analyzer. This MCA displays a gamma ray spectrum of every single photon coming out. And within just a couple of % accuracy, we know exactly what the photo peaks are. We can look it up in a book and determine what radionuclide it is pretty simply. Problem here is that the MCA is a very expensive piece of equipment, $30,000 or $40,000, and the crystal in it only works properly at liquid nitrogen temperature. And nitrogen tends to boil off pretty rapidly, so one has to constantly replenish the nitrogen. In other words, it's a pain in the neck to do it, but when you need a high resolution gamma ray spectrum, that's your only real choice. So A and C are possible ways to do it, and therefore choice E is the correct answer. Okay. What is the legal limit for moly breakthrough? Be very careful here. I'll let you read through all of them.
Is it choice C?
E.
I think I have a lot of answers here that are choice D today. That was not on purpose, but yes, choice D. It's 0.15 microcurie per millicurie. Now keep in mind, a millicurie is 1,000 microcuries. So we are finding an impurity, which is roughly 0.1 of a microcurie out of 1,000. That's 1 part in 10,000, and that's the upper limit. And we're able to do even better than that. And note this, here is where people make this error. It is at the time of administration of the dose. If I were making up the rule, I would have made it at the time of elution, because then you would never have to check it again for the rest of the day. But the federal government, in its infinite wisdom, has made it at the time of administration of the dose. And that means that either you, the technologist, or more likely the computer, has to calculate this for every dose of technetium on every patient all day long. Now, fortunately, we all have the computers that do it for us, and we don't need to do it. But just keep in mind, it's at the time of administration and not at the time of elution. It actually used to be 25 years ago, it used to be at the time of elution, and it was a totally different number. And I don't want to tell you what it was because you might remember it. So, but this is your right answer, 0.15 microcurie per millicurie. Okay, these are true false questions. We're going to go down the list. We're going to do A, B, and D first, and then we're going to come back to C because that requires a calculation. Let's say you eluted the generator this morning at 7 a.m. and you got a ratio of 0.1 microcurie per millicurie. Now, that's certainly an acceptable number at that point in time. It's lower than 0.15, so that's fine. Now, what happens to that ratio as a function of time? True or false? This ratio decreases as a function of time. Look at the half-lives. I hope you can see my image here. If this is technetium and this is molybdenum, the technetium is decaying rapidly while the molybdenum is decaying very slowly. So what happens to that ratio? Does it go up or down?
Up.
It is going to go up, and every batch of technetium will eventually fail the Molly breakthrough test. It might take 40 hours or 60 or 80. We don't care about any of that because after 12 hours by federal law, we have to throw it away anyway. You can't use it after 12 hours. So A is false. That ratio increases as a function of time. What if we eluted the generator 1 hour later? Initially it was 7. Now it's 8 a.m. True or false? No activity would be obtained.
False.
That is false. You're always going to get something. It might not be much, but you'll get something, and it takes 23 hours to reach the peak. Let's go down to D. Equilibrium is reached 12 hours after the previous elution.
False.
Totally false, 23. Now let's look at C. Would we be able to use this product at 10 a.m.? Now we eluted at 7 a.m., now it's 10 a.m. That's 3 hours, that's half of a half-life. So we want to do the calculation to see what happened to this ratio over the 3 hours. So here it is. The fraction fraction of molybdenum decaying after 3 hours, you'll recall from our math before, it's going to be 1/2 to the power of TLFs over T1/2. And that would be 0.9694. That's how much molybdenum remains in 3 hours. For technetium, it's going to be 0.5 to the power of 0.5, which is this number. If we take 0.1 microcurie per millicurie and multiply it by the decay factor of molybdenum divided by the decay factor of technetium, we come up with 0.137. Can we still use that? Is it less than 0.15? It is. Therefore, yes, we could still use that. You're not likely to get that as an exam question. Guess you never know, not likely. But if you do, you're simply going to decay 0.1 microcurie of moly with this factor, and you're going to decay 1 millicurie of technetium with this factor. Okay. For the existence of radioactive equilibrium, this is any kind of equilibrium. True or false? The half-life of the parent has to be greater than the half-life of the daughter. We know that's true. The number of atoms of the parent will always exceed the daughter. That's always going to be true because the daughter is going to be decaying faster than the parent. parent must decay to a metastable state. That is false. We prefer that it be a metastable state so that nothing is coming out of it but gamma rays. But many of the products of the generator are not metastable states. Finally, if the daughter is stable, you don't even have an equilibrium. So choice A and B are true and the other two are false. All right. In transient equilibrium, the ratio of parents' half-life to daughter's half-life is approximately
B.
it's going to be 10, remember, for transient 10, and for secular, it'll be a really big number. Okay, now, any questions about that test? Okay, if not, I'm going to back up now and show you those 8 slides that I created for you just yesterday. So this is about the strontium rubidium generator. I would not be surprised if you get questions on it because there are hundreds and hundreds of facilities in the United States that are using this generator for performing cardiac studies. The reimbursement is such that if you are doing 10 studies a day or more, it's actually more cost effective to use this generator than it is to use something like Cardiolite or MyoView. So the parent in this generator is strontium-82. It decays by electron capture and beta plus decay to rubidium-82. And that's the diagnostic drug that we are going to be using, rubidium chloride. We're using it for PET imaging because this is a positron emitter. And we can do it under pharmacologic stress, but not really under a treadmill kind of stress. It really needs to be pharmacological. Part of the reason for that is that no one has really developed the really good software for image processing. So what's in this generator? The strontium is the parent, and just like molybdenum was bound to aluminum oxide, here the strontium is bound to tin oxide, stannic oxide, and of course the column is lead shielded, just like in the technetium generator. And that generator provides a way for us to elute the rubidium and obtain it in sterile and pyrogen-free form. A lot of record keeping is involved here, and unlike the Molytech generator, which is very easy to use, this is very complex, and you'll see from a diagram that's coming up shortly how complex. There's a lot of record keeping involved. We have to track the eluate volume, and when it reaches 17 liters, that's a lot, but when it reaches 17 liters, you can no longer even use the generator. Also, the quality control testing is going to check for the amount of rubidium, that's your desired product, the amount of strontium, that is the parent, you hope that's not there. And in some rare cases, strontium-85 could also be there. So these are the 2 radionuclide impurities that we have to check for. And these are the limits of them. I'm not going to make a big deal over this. I doubt they would ask you the limits, but you can see they're very tiny. The limit for strontium-82 is 0.02 of a microcurie. That is just 20 nanocuries. And this is 0.2 of a microcurie of strontium-85. That's 200 nanocuries. So very, very tiny amounts. Also, remember that the column here has stannic oxide, and so I guess it's possible for some tin to be moved off the column, and the limit is 1 microgram per milliliter. Now, tin is not very toxic. We inject 1,000 micrograms into patients every time we do a MUGA with stannous pyrophosphate. Now, here's some technical information about rubidium-82. As I mentioned earlier, it's a positron emitter. 95.5% of the time it decays by positron, and 4.5% of the time it decays by electron capture. And look how short the half-life is, 75 seconds. That's an important number to know, because when we look at the next couple of slides, you should be thinking how perfectly everything has to go. There is no way to recover from something that goes wrong with a rubidium study. So both of these, you remember, EC and beta plus are competing modes of decay. They both had arrows that came from right down to left. One was a broken arrow, one was a straight arrow, but they started and ended in the same places. And so they're competing modes. And the positron decay results in annihilation radiation. And look how much lead it takes to shield this. The attenuation factor is 0.5. That means that only 50% goes through it. That is by definition one half value layer. So the half value layer is 0.7 of a centimeter at 7 millimeters. Not real thick, but take a look at this. 10 to the minus 1, that's 1/10. That's 1 TVL, a 10th value layer by definition, and that's 2.3. And to reduce it from a 10th to a 100th to a 1,000th and to a 10,000th, we're going to go from roughly 2 to 5 to 7 to 9 centimeters. 9 centimeters is pretty thick. It's almost 2.5 inches of lead. That's a lot. So very penetrating photons, and shielding, of course, is going to be a big problem. And that's why the generator is very, very heavy. Has a lot of lead inside of it. Now there's an infusion system, a very complex one. You'll see it shortly in the diagram that goes with this generator. It's all an integral part. The generator costs, I do believe, somewhere between $30,000 and $35,000 per month. But if you have a very busy department doing lots of cardiac studies, it's sometimes more cost effective than buying Cardiolite or MyoView. And so that generator has to be able to calibrate the dose, and the dose is literally flowing into the patient during the calibration. The dose is higher than anything you have probably ever seen injected. 40 millicuries is the recommended dose, but you could go up to 60 if you have, for example, a very large patient, maybe somebody who weighs 250 or 300 pounds. So you're going to have to give more because of attenuation. So, but this is the range, but this is a recommended dose. And the dose is administered as it flows from the generator directly into the patient at a flow rate of 50 milliliters per minute. That's a big 60 cc syringe, almost filled up, and it's going straight into the patient in 1 minute. And of course, it has to be a catheter of some kind that's inserted into a fairly large vein. Usually an anticubital vein would work fine. This is a photograph of the generator here, CardioGen 2. And this is a schematic down on the bottom showing you all the different parts and the different controls that are involved here. You can see here the sketch of where the column is, where liquid is coming down this column on the right through the tin oxide, removing the rubidium, coming up here, and it's normally in a technetium generator, we would collect it, but here we don't collect it. It goes into the outlet line, and that would be probably right here at the bottom of the diagram, and that goes through a valve that goes straight into the patient. And there's also a waste bin to collect any excess that is not injected into the patient. So this is not a simple operation. It requires a pretty fair amount of training to be able to competently initiate and run this kind of study. Just 2 more slides and we'll be done with this very quick review of the strontium rubidium generator. For rest imaging, pretty simple. I actually had one of these many years ago when we were testing the generator in our department, and everybody in our apartment was volunteered by my boss and said, "You're going to be a volunteer. Show up tomorrow at 10 o'clock. So all of us got a 40 millicurie resting dose of rubidium, and everybody in the department had a normal scan except for one person who happened to have been my boss's wife. And the reason her scan was abnormal is that she had been treated for breast cancer with adriamycin, which causes cardiac toxicity. And she had the only abnormal study of anybody who was tested. So this is pretty simple. You'll see in a moment how it works. we give the injection, we wait 60 to 90 seconds. Now, what was the half-life? 75 seconds. That means that while we're waiting those, let's say 75 seconds, we just lost half our activity before we ever start the camera. So that's one of the reasons you have to give so much. You injected 40 millicuries, 20 millicuries is already gone in 75 seconds. And then we image for 5 minutes. So think about this, 5 minutes of imaging, plus there was 75 seconds of waiting. So we have a little over 6 minutes. That's about 5 half-lives of rubidium. And what fraction remains after 5 half-lives? 1/2 to the 5th. That's 1 over 32. That's 3%. That means that 6 minutes down the road, 97 point something percent is gone already. For stress imaging, first thing we have to do is we have to wait at least 10 minutes after completion of the rubidium study. That's just to make sure that all the rubidium is gone. Then we will give the pharmacologic stress agent, whatever the physician chooses to use, in accordance with the prescribing information. And then we will repeat what we did before. Give the pharmacologic stress, we wait the 3 minutes, we give the rubidium, we wait the 60 to 90 seconds and start the camera. And after 5 minutes, we are done. Okay, that's a quick but comprehensive overview. The material I started with was 15 pages long, and I removed everything that I thought was not necessary for you to see today. Any questions about the strontium rubidium generator from anyone? Okay, good. If not, we're going to advance to the remainder of radioisotope production. We spent a lot of time on generators, and there are 3 other kinds of reactions. We're going to spend a total of perhaps 5 minutes just covering these 3. There's almost nothing we use today that's made by a thermal neutron reactor. This is a reactor where thermal or low energy, relatively slow moving neutrons bombard a target. This is called an N-gamma reaction. Neutrons in, that neutron goes in the nucleus and stays there. The gamma is ejected. And here's how molybdenum used to be made, not anymore, but molybdenum 98, dug up from the soil and purified, was bombarded with neutrons, and it made molybdenum 99. This neutron just went into that nucleus and added 1 to the atomic mass, but didn't change the Z number. It's still molybdenum, chemically identical, but we almost never use this reaction for anything anymore. I'm going to skip the next 3 slides. I think they're not too important. This is a very important one here, fission reactor. And here's what happens. Uranium-235 is what is called fissile, F-I-S-S-I-L-E, or fissionable material. We bombard it with a neutron, it becomes uranium-236. And then that splits into 2, I hate to call them halves, 2 parts. And it produces 2.4 neutrons for every neutron in. So after this reaction gets going, it's actually self-propagating. You can take the neutron source away and it just keeps on going. The fission products have atomic masses of around 100 and around 135. And there probably are 50 different nuclides produced by the fission reaction, but we in nuclear medicine are only interested in 3 of them. And so your exam question would be, what are the 3 fission products that are used by nuclear medicine? Now, a number of these have other medical applications, but not nuclear medical applications. So here's your exam question. What are the 3 fission products? So let's think about this. What do we use that has a mass of around 100? What do we use that has a mass of around 135?
Xenon
Good,
and I-131.
good. And what's near 99?
Molybdenum.
I'm sorry, what's near 100? Good, molybdenum, terrific. So there they are. We have molybdenum near 100 and iodine and xenon near 135. And all the molybdenum in the world today is produced by the fission reaction. 30 years ago, it used to be provided by that first reaction I showed you, the thermal neutrons. Not anymore. And finally, we want to talk about cyclotron. There are 6 cyclotron-produced isotopes that we use today. And a cyclotron is a source of very high energy particles. But keep in mind, it has to be a particle that can be charged or accept a charge. That means not neutrons. Neutrons would not work. You can have protons, deuterons, that's a deuterium atom, tritons, that's tritium, alpha particles, helium, hydrogen atoms. There are a lot of things that can accept a charge. And here are a few reactions. There are probably 40 or 50 reactions that could take place. Here's a simple one, a DN reaction. We bombard with a deuterium, out comes a neutron. Here's an interesting one, a P5N reaction. Commercially has been used to prepare iodine-123. 1 proton goes in the nucleus, and out come 5 neutrons. That's a pretty spectacular change. It really is, to put in 1 particle and get out 5 of them. And the net effect is always going to be that we're going to end up with a different element. For example, if we wanted to make oxygen 15, we would take ultra pure nitrogen 14 from the air that we're breathing right now, bombard it with deuterium, out comes a neutron, and it makes oxygen 15. These are different elements. We can always separate different elements from each other. There's always going to be a chemical or a physical way to do it. We can never, ever separate isomers. We can even separate isotopes. The Iranians, in fact, are doing that a lot right now by separating plutonium 230, I think it's 237 from 235, also uranium. So what does cyclotron yield depend upon? How much target do you have? And the targets are really pretty small. They're usually micrograms, milligrams, not larger than that. The energy of the particles is critical. There's a threshold level. It's like, can you boil water at 98 degrees centigrade at 1 atmosphere? The answer is no. You could heat it at 98 degrees forever, it'll never boil. But once it gets to 100 degrees, it will boil. Same thing is true here. There's a threshold energy for every reaction, and it's a huge number. It's usually like 38 or 50 million electron volts, not K, but MeV, million electron volts. So if it's 38 and you're operating at 37, the reaction's not going. It's got to get to that threshold, and then it takes off. We're concerned about how rapidly the daughter decays, not the daughter, but the product decays compared to its formation. How long do we irradiate? There's a certain period of time where the curve goes up like this and reaches a plateau. And that's the equilibrium point where it's decaying as fast as you're forming it. And that's when you stop. And finally, and this is an important thing, isotope enrichment. Remember back here, I told you that we took soil, we enriched all the molybdenum so that we got only molybdenum 98. We got rid of molybdenum 97, 96, 95, 100, 101, 102. We've enriched it. That's called isotope enrichment. And that is what we have to do. Now, how does the cyclotron work? There are week-long courses in how it's going to work. You're going to get about a 2-minute course in how it works. There are huge copper plates. They're probably 5 or 6 feet tall, shaped like the letter capital D. And there are 2 plates that right next to each other with a little air gap between them. And the particles are accelerated by having the charge on the plates oscillate back and forth from plus to minus, but like hundreds of thousands of times per second. And so that helps to accelerate the particles. And we're using a magnetic field to keep them in pretty much circular motion. And as we ramp up the electrical current, that makes the particles more and more energetic. And when they finally reach the desired energy, then we let those particles come out of a port, and the beam aims at the target, and creates the product. Separation techniques I'm not going to discuss. No one's going to ask you that. But here's a good question. There's a list of 6 cyclotron-produced isotopes that we use all the time. You're familiar with every one of them. 5 of them we use in patients. 1 of them we never use in patients. Who can name some of the cyclotron-produced isotopes?
Gallium.
Good. Thallium,
Gallium.
gallium. Good.
Indium.
Here's a good way to remember that. Anything ending in IUM, not
Right.
rubidium, but everything else.
Mhm.
Thallium, gallium, and indium, they have a lot in common. They're all cyclotron produced. They all decay by electron capture, and they all have a half-life pretty close to 3 days. What are some of the others? There are 3 more.
F-18.
Good. So here they are. F-18 is on the top of the list. Here are your 3: gallium, thallium, and indium. This is 67-hour half-life. Sorry, gallium is 73, indium is 67, and thallium is also around 70. So these 3, gallium, thallium, and indium, have roughly the same half-life. Fluorine-18 is 110 minutes. Iodine-123 has a half-life of 13.3 hours. And cobalt is in this list because it's cyclotron produced. What is the principal utilization of cobalt-57 in nuclear medicine? What do we do with it?
Sealed
Quality
source.
control.
Exactly. It's for sealed sources. It's a flood source for performing quality control on gamma cameras. And it's also one of the dose calibrator sources that everybody uses because it simulates technetium and energy, 122 versus 140. And we make the assumption that if our equipment works with cobalt, it's going to work with technetium. Pretty valid assumption. Now, those are the 6 that are commonly used. If you have your own cyclotron, there are 3 isotopes that you can produce on site. We, of course, don't have our own, but the University of Chicago does, and there are some other Massachusetts General, there's some other big hospitals that do, and here they are. Carbon-11, nitrogen-13, and oxygen-15. It's kind of easy to remember their half-lives because 20 equals 10 times 2. They're all minutes. And these are all cyclotron produced, and it's very easy to perform chemistry with these isotopes. In fact, Massachusetts General Hospital does a significant number of their cardiac scans with nitrogen-13 ammonia, very high quality scans. And carbon-11 has been bound to some molecules that are useful for looking for prostate cancer. Okay, let's take that mental breather now. We have finished with isotope production. We're going to start radiopharmaceuticals, and we at least want to get through the basics today. If we don't finish that today, that's okay. We'll finish it up next week. And then next week, we are hoping to start the clinical utility of every single radiopharmaceutical sold in the United States. Okay, before we start this, are there any questions from anyone about isotope production? Anyone? Okay, radiopharmaceuticals. So the first thing we want to do is define radiopharmaceutical. And you're going to see shortly that there are many differences between a pharmaceutical and a radiopharmaceutical. So here's the official definition. It is, of course, radio and pharmaceutical. It's a radioactive drug, and we administer it for either diagnostic or therapeutic purposes. And one of the things to note is that unlike drugs that patients take every day and even administered in hospitals, our drugs typically don't elicit any kind of response from the patient. They don't feel anything. If you have a saline injection in one arm and thallium in the other, you would never know which is which. You just wouldn't. I've had a bunch of nuclear scans myself in my lifetime, and you cannot tell anything from the injection. You feel absolutely nothing different than if it were saline. Now, here's a little comparative chart, and this should be very helpful to give you a sense of the other differences. Pharmaceuticals are, of course, not radioactive, and radiopharmaceuticals are, and they will confer a radiation dose of some kind. Might be small, might be moderate, but there will be a radiation dose. The drugs that people take, like penicillin, most of the time they're taken orally, and we often see something like this. Take this drug 3 times a day for 10 days, or people who take antihypertensive medications, take this twice a day for the rest of your life. We don't have that. In fact, very few things are administered orally other than radioactive iodine or perhaps radioactive scrambled eggs. Everything is by injection. Most of the time intravenous, could be arterial, like in the case of microspheres, but mostly it's intravenous. And typically it's in single injection. The one exception I can think of to that is when we perform a MUGA, we always do 2 injections. The first one is the stannous pyrophosphate, and then the second one is the pertechnetate. But typically, there's 1 injection. Pharmaceuticals that people take every day, often toxic. Look at aspirin. There, 10 or 15% of the people in the world can't take aspirin because of gastric distress. Our drugs are rarely toxic. They rarely cause adverse reactions. So we don't expect any kind of effect. And in fact, there's an adverse reaction registry run by the Food and Drug Administration, and people all over the United States submit reports whenever they encounter an adverse reaction. Take a look at the bottom right sentence. The adverse reaction rate for drugs used and approved by the FDA, it averages around 2 per 100,000 administrations. That's an incredibly good safety record. One or two in 100,000 administrations. On the other hand, almost every drug we ever encounter can cause adverse reactions. There are new drugs that are advertised now in magazines, and you say, oh boy, that drug could really help me with this disease. And then when you take a look at the adverse reactions that often include death, you say, gee, I don't think I want to take that drug. So that's something we just don't have to deal with, adverse reactions. I've seen something before, by the way, where it's not really an adverse reaction. It wouldn't even be reportable, but we've seen patients who have either a needle phobia or a phobia of being injected with radioactivity. And I've seen people faint when you put the needle in their arm before you do anything to them. That's not an adverse reaction. That's a psychosomatic reaction. And no one should be reporting that as an adverse reaction. Now, here's a good exam question. It is well known that the chemical thallium, like in the form of phthalocyan, is very cardiotoxic. Just like an overload of potassium can stop your heart, an overload of thallium can also stop your heart. It's very cardiotoxic. So why are we not concerned about giving a patient 3 millicuries of thallium intravenously, someone who is already sick with heart disease? Why are we not concerned about that? Now we're talking about chemical toxicity here. We're not talking about radiation dose. We're simply saying we know thallium is cardiotoxic. Why is it okay to inject it into veins?
Is it because it's a small dose?
Good. How do you mean that dose? You mean on the mass of thallium that we're injecting?
I guess, yeah.
Say yes. That-
Okay.
That is the correct answer. Okay, so here's why. We're not worried about injecting thallium because if you do the calculation, a 3 millicurie dose of thallium is only 40 nanograms. You evaporate 40 nanograms to dryness, you can't even see it. 40 nanograms would not be harmful even to a baby. 40 micrograms wouldn't be harmful either. So we have a huge margin of safety for thallium. So we're not at all concerned about chemical toxicity because the mass that we're injecting is just very, very tiny. Now, when we as radioisotope chemists design a new radiopharmaceutical, there's a list of the properties of the ideal pharmaceutical. We're going to take a look first at the list of the properties of the ideal diagnostic And then we'll take a look at the list of the properties of the ideal therapeutic. They're going to be pretty much totally opposite. Number one, for diagnostic, what do we want? We want a pure gamma ray emitter. We don't want alphas and betas. We're doing a diagnostic study. How helpful are alphas and betas? Zero. An alpha can't escape the patient's body to be imaged, and betas pretty much can't either because their penetrability is only a few millimeters. So all that they do is, because of their high LET, they confer a significant radiation dose to the patient, and they're not imageable. We just don't want them. We want a pure gamma ray emitter, and this is an empirical finding. The ideal energy range is considered to be 100 to 250 keV. That's where our cameras operate the best. That should not be a surprise because this range is optimized around technetium, our so-called workhorse of nuclear medicine, and I-123 and indium, and things are in that range of perfection. We work outside that range sometimes. We don't like to because, as you'll see in an upcoming graph, the image quality drops. If the energy goes too low or too high, the image quality drops. So we want to be here 100 to 250. Now, some books say 100 to 200. I think you get the point, though, that 100 is the lowest, 200 to 250 is the highest. And here are some of the examples of where we're outside that range. Thallium is 71, xenon is 80, well below 100. In fact, thallium is about the lowest you could go and ever hope to get even a semi-decent image. And what about above 250? We have I-131. Sometimes we're forced to use that isotope, like on a whole body iodine scan, and we're going to get suboptimal image quality. Now, here's a diagram that I just kind of created this. It's not from any particular study, but here's the plateau where you are going from 100 to 250 keV, and the image quality is as good as it's going to get. And look what happens is the energy goes from 100 towards 0, the image quality drops very rapidly. And when the energy goes from 250 on up, the image quality again drops very rapidly. So we want to be right here on the plateau with one exception, and that is this. What's going on here? We would have expected this line to go down to the baseline and forever keep going. But there's a big spike here at 511 keV. What are we doing there?
PET.
Sure, that's PET scanning. That's annihilation photons. So that's a totally different kind of imaging system, not a regular gamma camera, but a PET scanner that can deal with 511 keV photons. A regular gamma camera cannot. It just goes, the energy just goes right through the crystal. It doesn't deposit much at all. So this is the one exception here, PET scanning. Otherwise, we want to be 100 to 250. Now, this is the third of the ideal properties. The T effective, we want ideally for a T effective to be a little bit longer than the duration of the study. And 1.5 is the number that most people feel is correct. Now, let me define test duration for you. The test duration begins the moment you inject the patient. And the test duration ends when the doctor looks at the study, looks at the films, looks at the images and says, okay, you can let the patient go home. That's the test duration. And we want it to be 1.5 times the T effective. The reason we want it longer than that is that, as you all probably know by now, things go wrong occasionally. The patient might move so much that you say, got to restart that acquisition. Or maybe your computer goes down and you have to reboot it. Or there's a camera problem. You need some recovery time. And this gives you some recovery time for any study they're going to do. Now, let's take a look at a couple of examples. One is perfect, one is not. A bone scan for, let's say, MDP, the T effective happens to be equal to T physical because the biological half-life of those phosphates in bone is pretty long. And so the T effective is 6 hours. It's a 4-hour procedure, right? We inject, we say to the patient, go away, come back in 3 hours, and then we scan. So we have a ratio of T effective of 6 divided by procedural length of 4, 1.5, perfect. But look at a liver scan. It's a 1-hour procedure. Again, by coincidence, the T effective happens to be 6 hours. T biological is infinitely long. So in that extreme case, T effective equals T physical. So the ratio here now is T effective over procedural length is 6-to-1. Now, that is simply not ideal. It's not what we want, but that doesn't mean it's not a valuable procedure. It simply means that the radiation dose is going to be higher than we want it to be, and the patient will be radioactive longer than we want it to be. But even though it's not ideal, a liver scan is still a valuable procedure under some circumstances. We don't do it so much anymore because CT is so good at that, but on occasion we do a liver scan. So this is the case where the ratio is perfect for bone scan and quite imperfect for the liver scan. Now, how do we want things to clear? Things actually clear logarithmically, like this sloped line coming down. That's the way things really happen. That's actual clearance. But the ideal clearance pattern would not be a curve like that. It would be like this, where the dose is administered, it stays in the target organ till the moment the test is done, and then boom, it drops off a cliff. There is only one study that we have that approximates that ideal clearance pattern, where the activity is constant in the target organ, and then it departs all at once. What procedure is that?
Xenon?
Say it again.
Xenon?
Yes, good. That's a xenon ventilation study. Here's the breath holding phase. And patient inhales, holds his breath for this long, and then he exhales. Now, he's not exhaling all of it that instant. We know that because we look at washout for the next couple of minutes, but nothing comes closer to this ideal clearance pattern than a xenon ventilation study. This is a very important fourth factor. Now, these 4 factors are the ones that are really not so intuitive. And then we're going to look at several factors that are just common sense. We want a high target to non-target ratio. That means that the counts per minute per area in the target have to be high compared to the surrounding tissue. The minimum ratio is 5-to-1. I don't care how good a film reader a physician is. If the ratio goes below 5-to-1 on planar imaging, it's very likely the one is going to miss the diagnosis because the ratio is just not high enough. We don't even want 5-to-1. We're settling for 5-to-1. We want 25-to-1 or 50 or 100-to-1. We don't get that most of the time, but that's what we want. For ECT, you know this is a SPECT study. This is emission computed tomography. Compare that to CT scanning, which is transmission computed tomography. We are collecting photons that are being emitted from the patient's body. And so because we can do a better job with resolution, we can deal with a 2 or 2.5 or 3-to-1 ratio minimum for computed tomography. But remember, we want that really big ratio. It's very important for detecting lesions and determining things like myocardial perfusion scanning. If that ratio is too low, what happens is we end up with a non-diagnostic study. That's got nothing going for it whatsoever. You have to repeat the study at no charge. The referring physician loses confidence in you because you can't do a bone scan or a heart scan. Increased radiation dose, increased discomfort. It's got nothing going for it whatsoever. Now, let's take this target and non-target ratio a little higher. When we're doing a bone scan, we expect to see bones. What would be the target and non-target tissues on a bone scan? I'm going to give you a hint here. There actually are 2 different ratios we're going to deal with. We expect to see bones. That's the target tissue. What would be the non-target tissue?
Soft tissues?
Good. All the soft tissue in the body. So we want to see bones against soft tissue. We want to see that. But where are the lesions? Are they on the bone or in the soft tissue?
Oh,
They're on the bone. And so we also need a bone to soft tissue ratio. I'm sorry, a lesion to bone ratio of 5:1. Remember, we want a 5:1 ratio of bone to soft tissue. We want a 5:1 ratio of lesion to bone. And if we have both of those, look what happens when we multiply them. If the bone to soft tissue ratio is 5:1 and the lesion to bone ratio is 5:1, and we multiply them, this gives us a lesion to soft tissue ratio of 25:1. This is why you can walk into the reading room, stand 20 feet from the view box and say, that guy has metastatic bone disease. How can you do it? Because the lesion to soft tissue ratio is, and also the bone is very high, very easy. I've given some presentations to high school students, showed them a bone scan. They know nothing about nuclear medicine. They take one look at that and say, ooh, that looks awful. They don't know what it is, but they know something is wrong. And the reason they know it's wrong is because of that lesion to soft tissue ratio. So let me back up one step. It's very important. This is that fourth thing we need to keep in mind. Very important to have that high target to non-target ratio. Now, these are the common sense things that you would have thought about. Minimal radiation dose to the patient and minimal radiation dose to the nuclear medicine technologist who is in close contact with that patient, injecting the patient, imaging the patient, and so on. Now, who are we more concerned about today? The patient who got the injection or the nuclear medicine technologist? Who are we more worried about?
Technologist.
That's correct. We're worried about the technologist. Number one, there's nothing we can do about the patient except make sure we give the smallest dose possible, meaning the smallest injectable dose possible, meaning the smallest radiation dose possible, consistent with a high quality scan. We have no way to really reduce the patient's dose, but we're not too worried because many patients get one injection in a lifetime, but the technologist is standing near patients 8 hours a day, 40 hours a week for years on end. And so the cumulative radiation dose to the technologist is of a lot more concern to us than a single dose to the patient. And yes, the patient certainly got a bigger dose today, but we're more worried in the long term about the technologist. Also, this is a common sense thing. The drug needs to be inexpensive and readily available. If it's too expensive, some doctors simply won't order the procedure. And also, if it's too expensive and insurance doesn't cover it, the patient will say, I can't pay for that, too expensive. And also readily available, that of course is common sense. Now, those are the properties of the ideal diagnostic. Just a very fast review. The first four were pure gamma emitter, a fixed energy range of 100 to 250, the T effective 1.5, we want the T, let's go back here to this one, the T effective to be 1.5 times the test duration, and then the target to non-target ratio. Okay, any questions about the diagnostic side? Now let's take a look at therapeutic. Now let's think first of all, what do we want to do diagnostically? We want to do no harm to the patient, which we really don't do, and take a picture. What are we trying to do therapeutically? We want to kill tissue and we don't care about taking a picture. So everything is going to be backwards. What did we say for gammas? We wanted pure gamma ray for diagnostics. Here, we don't particularly want gammas. We'll take them. We really don't want them. We want a pure beta emitter, or even today with radium, an alpha emitter. We want particles. They have a high LET. They're good at damaging tissue. And while we can take those high energy X and gamma rays, they don't confer a very high dose. Take a look at iodine-131. 90% of the tissue damage is caused by betas, not by the gammas and X-rays, even though there might be more gammas and X-rays. Secondly, what do we say diagnostically? 100 to 250 keV. That range came from the fact that we're using a piece of equipment to form an image. Here, there is no equipment. We're injecting or giving an oral dose to the patient, saying, goodbye, go home, good luck. We want the highest energy we can get. We want beta particles that are 1 million electron volts or higher. We want alpha particles that are 5 million electron volts or higher. We want big numbers of energies, not 100 keV, but 1 million electron volts or more. And so some of the therapeutic isotopes happen to be imageable by coincidence, like I-131, like samarium-153, but most of the time we don't use that property. So far, here's what we've got. Particulate emitters, very high energy. Now, this is a very vague term, moderately long T effective. What does that mean? I'm going to try to quantify that for you. That's like saying my coffee is weak today. You might think it's strong, I might think it's weak. That's a very vague term. So for us, a moderately long T effective for a therapeutic is measured in days, not minutes, not hours, not weeks, and not months. We want it to be in days. Here's a perfect example. When we treat a hyperthyroid patient with I-131 sodium iodide, the T effective happens to be 6 days. That's considered perfect. The patient doesn't think it's perfect because we tell the patient, you're not going to feel better for about 4 to 6 weeks. Remember, this iodine has a 6-day T effective, and after it goes through 30 days, that's 5 T effectives. At that point in time, a significant part of the radiation dose has been conferred onto the patient. So we don't want the patient cured in 1 day. The patient might want it, but we don't, because that is an acute, large radiation dose, and it can cause damage to DNA that does not even occur when the T effective is moderately long. So we want that dose stretched out over many days so that we don't confer too big an acute dose and harm the patient. And finally, target to non-target ratio. Now, let me pose this question to you before we look at that slide. Where are we more worried about target to non-target ratio? A diagnostic scan, a therapeutic scan, or are we equally worried? Diagnostic, therapeutic, or equally worried about target to non-target ratio?
Equal.
Definitely not.
Therapy.
Sure. Here's why we're worried about therapy and the ratio. If you were to administer a therapeutic to a patient, and let's say it went to the wrong place, like indium has been known to break off molecules and go right to bone marrow, you could kill a patient by injecting a therapeutic that might be in the wrong chemical form or something weird just happened. You could really harm the patient. You could blast his bone marrow with a huge dose. You can't harm a patient diagnostically no matter what you do. You're not injecting enough millicuries of a therapeutic. You're injecting a fairly low dose of millicuries of a diagnostic. You can't harm anybody. Here, the potential for harm, I won't say it's significant, but it's always there. And in fact, one of the things we have to make sure of, look at the last sentence here, we have to make sure that the therapeutic drug is in the right radiochemical form so that it will go to the right place. So it is very important to have that very high target to non-target ratio. We want it to be a big number, like 25 or 50 to 1. Now, those are the properties of the ideal therapeutic. And again, here are things that are common sense. Now, this question is going to have a different answer than it had before. We're always concerned about radiation dose to the patient. We want it to be minimal, except to the target organ. And what about the nuclear physicians who are administering therapy doses? They are, I know in my hospital, they are administering probably, oh gosh, several thousand doses a year, maybe 1,000 or 2,000 doses a year. I don't think it's that many, 50 times 10, more like about 500 to 750 doses a year, but still that's a lot. And there are only 3 physicians who are giving those. And so they are standing near patients who have I-131 on board, and there's no way to really protect yourself from them. You can't put the patient in a lead shield. And so who are we more worried about here? The patient, the nuclear physician, or both of them? And here the answer is going to be both of them, because our nuclear docs are going to be near I-131 often. Even if they're giving a capsule where the patient takes a capsule, swallows it, and is done in 5 seconds, and you move away, that's still 150 millicuries, is still a big blast to the dose administrator. Also inexpensive and readily available. I can tell you today, none of the new therapeutics is inexpensive. To give a course of 6 doses of the alpha emitter radium-223, it costs somewhere between $90,000 and $100,000. And we're talking about a drug that palliates pain, but is not curative. That's a huge price to pay. Also, yttrium-90 microspheres, very expensive, $15,000 or $20,000 per dose, times there's almost always 2 doses. We're looking at big bucks. I-131 solution or capsules, pretty reasonable in the big scheme of things. You can cure hyperthyroidism for probably a couple $100, not that expensive. Okay. Now, let me ask you if you have any questions about properties of the therapeutic before we continue. Anyone? We will, by the way, near the very end of this series, have a whole hour-and-a-half lecture on radionuclide therapy. Then we'll go into great detail into a lot more than we've talked about today. Okay, this next lesson here is more a pharmacy lesson than a radiopharmacy lesson. But there'll be a little bit of radiopharmacy in maybe the 3rd or 4th slide. Number 1, everything that we inject, radioactive or not, everything we inject parenterally into a vein, into an artery, must by law be sterile and pyrogen free. How do we define sterility? That's the condition in which there is no living thing, no life form in the injection. That could include the obvious things like bacteria, fungus, and molds, and also viruses. Even a spore that could evolve into something must not be there. So if it's sterile, no life forms. If it's sealed up in a vial and it's sterile today, it's sterile 50 years from now. Pyrogen-free means it contains no substances that cause fever. It is today illegal to administer anything parenterally in a vein that is pyrogenic. And it's especially toxic intrathecally. Many years ago, I would say probably in the 1970s, there was an injection of pyrogenic indium DTPA into the cerebrospinal fluid of a patient. No one knew it was pyrogenic because back then it was not required to test for it. And so they injected this into the CSF of a patient, and within 4 minutes, the patient had died from respiratory and cardiac failure because pyrogens are 1,000 times as dangerous put into CSF as into the peripheral circulation, like an arm vein. Even if something is pyrogenic and we injected it peripheral vein, the most it's likely to do is cause a fever, and the patient might not even notice it if you're not monitoring his temperature. So everything injectable must be sterile and pyrogen-free. Secondly, let me back up. Here's the term, must be. This is the term, should be. We can work around salt concentrations that are not equivalent to 0.9% sodium chloride. If it's very, very salty, like sulfur colloid, we call that hypertonic. If the salt concentration is too low, that's hypotonic. If it's just right, it's isotonic. We can inject things that are not isotonic if we do it slowly. Also, we had a drug, an investigational drug back in 80s, 85 or so. And it was only stable outside the body in 10th molar hydrochloric acid. I injected probably 200 patients with 10 molar hydrochloric acid. And guess how many of them had a reaction? 0, because the injection was done over 1 to 2 minutes. It was not just pushed in like we tend to do with other drugs. And so you can deal with things that are not a physiological pH, like a value of 7.4, something like that, are not isotonic if you do it very, very slowly. That's not ideal, but sometimes we have no choice. Now, this is your radiopharmacy part, a very important slide, mainly because this number changed back in 2006. And here's what it says. All injected doses or administered doses must be within 20% of the prescribed dose. It used to be 10%, not anymore. And there are still books out there that say 10%, and I will assure you that number is totally wrong. It's 20% plus or minus. That means that if you underdose a patient, and let's say you're 25% underdose, that's equally as bad as a 25% overdose. They're both violations of the law. Now, if it's underdose, you can recover by injecting more. If it's an overdose, tough luck. You can't really fix that. Now, Illinois, where we practice, happens to be an agreement state, and probably most of you who are listening practice in an agreement state. The bottom half of the United States, it's all agreement states. And so in an agreement state, you have the right to be more restrictive than in a federally regulated state, like the NRC. And so in our institution, we have chosen the default to be 10%. That's perfectly okay. You can be more restrictive, not more lenient. So remember that number, plus or minus 20%. That is the only percent that you'll deal with in nuclear medicine that is not 10%. Everything else tends to be 10%. We'll learn more about that in the NRC lecture. Okay, so now those are all the charts for the moment. And as you can see by the date here, this is pretty much outdated, but there aren't too many things I could add to it. What I want you to notice here is not the drugs. We're going to go through the big chart next week and cover every single drug that you need to know something about. It's more important to look at all of the different diagnoses here that we're working on. You know, a lot of people say, oh, all you do in nuclear medicine is cardiology and oncology. And nothing could be farther than the truth. Look at some of these other indications. We've had drugs for diagnosis of deep vein thrombosis, brain perfusion studies, abscesses and inflammatory sites, renal function, breast tumor imaging, several drugs for myocardial perfusion, a drug that came and went, but it diagnosed small cell lung carcinoma. And there are a few others now. There's another colloid that's on the market, Lymphoseek, that's not on this list. These are all just technetium products. And then here are some other drugs listed. None of these is technetium. They're all other isotopes. And more of these tend to be oncologic in nature, but not all of them. There are neurological drugs like DaTscan and Amyvid for evaluating Alzheimer's patients, FDG for almost every kind of tumor that occurs in human, except for two in particular, renal cell carcinoma and prostate cancer. No one should be using FDG for either of those. Strontium chloride and samarium EDTMP and radium chloride, those are all approved for palliation of pain. Zevalin for non-Hodgkin's lymphoma therapy. Myosint came and went, but it was good for acute MIs. Prostate cancer drug that's now off the market. Fluciclovine is what we would use today. It's not on this list. Needs to be updated. Bexar is gone. And red cell labeling with technetium. So that's a pretty long list of indications, and they're not at all just limited to cardiology or oncology. Now, there are two different kinds of studies that we perform. First one is a dynamic study, and I want to define that for you as a study where the image changes as a function of time. Now, that change might be in a second, it might be in 5 minutes, it might be in 30 minutes, but you will see the image change as a function of time. And the first two here have very short cycle times. For example, cardioangiography is a cardiac flow study. You should be thinking technetium red cells, where we're doing a MUGA, and we're looking for all of these kinds of defects here, heart defects, aneurysms, dyskinetic, hyperkinetic, hypokinetic, akinetic areas of the heart muscle wall. And so what is our cycle time here? We are looking at the heart beating, and every cycle takes approximately 1 second, maybe a little bit longer. So we're looking, when we do a MUGA, we're collecting perhaps 1,000 heartbeats, but that you can watch that cycle right on the screen. You can watch the heart beating. You can see that one cycle is about 1 second. And here on a cerebral blood flow study, reason we do this is to diagnose cerebral death. These other things here are almost never done anymore. They used to be. So we have pertechnetate, and I know some people who use Ceratec to evaluate for cerebral death. And what is our cycle time here? We inject with the patient under the camera and the computer up and running, and we inject and we collect data over perhaps 30 seconds. And the physician is going to look at what's called a multi-formatted image, which has 60 half-second frames of time. So your cycle time here is very short. What you're looking at is what happened from 0 to 0.5 second, 0.5 to 1, 1 to 1.5, to 1.5 to 2, and all the way out to 29.5 to 30 seconds. So here, these two have very short cycle times, 1 second and even shorter. And they are certainly dynamic. We have all the cholecystographic studies. Today, we have these two drugs, dizofenin, that product was originally developed by DuPont, and mebrofenin. This is mebrofenin, you might know this as Colatec, and this was called Decida, or might be hepatolite. And this one, Hida, was lidophenin based on the lidocaine molecule. We'll take a look at that next week. And how many studies are performed in the United States this year with Hida? Anybody know? Here's a big hint. 0. Hida has been off the market for at least 25 years. People are still ordering Hida studies, and we all know what it means, but there's no way to do a Hida study because the drug is not available. These two are very equivalent in function, and they work very well, even up to a bilirubin level of above 20. Hida did not work above 8. So these are looking for obstructive disease and some other things that we'll take a look at next week. And the cycle time here, it's probably in minutes. Cisternogram, probably also in minutes, where we inject indium DTPA directly into CSF, and we watch the flow as it moves up the spinal canal and bathes the brain. We're looking for blockage and blockage somewhere in the CSF flow pattern or slow flow, and also hydrocephalus. Is certain forms of hydrocephalus that can be diagnosed with this. And in fact, one of the in vitro studies we used to do, and patients literally hated it, was we would inject the indium DTPA intrathecally and put what are called pledgets. They're little cloth strips way up into the nasal sinuses. Very painful putting them in and painful taking them out. But when you take them out and count them, you can find the smallest CSF leak imaginable. You could never find a leak this small with imaging. Only with counting those pledgets in a well counter. Here are some more. All the renal scans are dynamic. DTPA scan, a MAG3 scan. We probably are imaging over maybe 30 minutes, maybe a little bit longer, taking a look what happened from 0 to 3 minutes, 3 to 6, 6 to 9, and so on. So the cycle time here would be minutes. And what is the, we'll go in greater detail next week, but what is the route of clearance of DTPA? How does it clear?
Glomerular filtration.
Good. This is filtered by glomerular filtration. How about MAG3? And so MAG3 is what we call secretory function. The tubules secrete this drug, about 80% secretion. This is almost quantitative for glomerular filtration. Gastric emptying study. We are tracing a radioactive meal through the GI tract, usually out to as long as 90 minutes sometimes. And we have a solid meal, which would probably be ovalbumin. That's a fancy way of referring to egg whites. Ova is eggs, egg whites. A liquid phase meal, we don't do this too often, with India of GTPA put into either orange juice or water. And we trace this over time, and we can find either abnormally fast or abnormally slow gastric emptying rates. And again, we're going to delve into that at much greater detail next week. Pulmonary ventilation. This is a static and dynamic study. When the patient holds his breath, that's obviously static. The image is not changing. He's holding his breath. But the minute he exhales, it becomes a dynamic study where we are looking at washout. And so this is a combination of static and dynamic. And there are two different mechanisms associated with those. The static phase is called simple or passive, it's called compartmental localization. And the dynamic part is simple diffusion, where xenon can actually cross membranes in the lungs and get into the blood pool. Again, more of that next week. Leg venograms, we don't do this anymore. This used to be the most dreaded test that radiology residents got called in for in the middle of the night when they did it with contrast media, because they injected foot veins, watched the flow up the leg looking for a blood clot. And so many people had adverse reactions from the contrast media. They had palpitations, they had nausea, vomiting right on the table. Some of them had anaphylactic reactions. And so they loved it when we did it with technetium MAA, but now it's done with neither of those techniques, and it's done by Doppler ultrasound. And we never do this anymore. We haven't done one in 15 years. One of the bonuses of doing a leg venogram with MAA, there are two bonuses. One, you can find where the blood clot is. And also, if you want, for free, you can get a lung scan at the end, because you've injected it into the venous circulation. And we, in fact, did, many years ago, we did perform that lung scan. How about this one, avoiding cystogram? We use sulfur colloid. We push it through a catheter into the urinary bladder, and then we watch it empty, usually pretty rapid. These are almost always children's studies, not always, but almost. And we can look at whether urine is refluxing back up to the kidneys. Is the bladder empty completely or not? And this is a very valuable, very commonly performed study. The most difficult part of it is probably catheterizing the patient. Now, we can do avoiding cystogram in radiology also under fluoroscopic control. Which is a higher radiation dose? Filling up a child's urinary bladder with sulfur colloid, or performing a voiding cystogram in radiology under fluoroscopy? Which is a higher dose? Anyone? So
Sulfur colloid.
The fluoroscopy is many times as much dose as the sulfur colloid. First of all, for sulfur colloid, when we put in 1 millicurie. Secondly, how long does it stay in the bladder? Minutes. The T effective is very, very short. So the radiation dose into the bladder from 1 millicurie is usually 50 or 60 milligrams. Fluoroscopic study is 2,000 milligrams per minute of fluoro time. So even if the radiologist is terrific and does it in 1 minute, that's already an internal dose of 2,000 milligrams compared to 50 or 60. It's 40 times as much. I'm not knocking fluoro at all, because fluoro provides a lot of anatomical information that we can't do. We're not good at anatomy. We're good at function. And I see these as not competing studies, but complementary, where we're really good at the function, and fluoro is really good at the anatomy. Now, any questions about dynamic studies? This is not every single possible one, just to give you an overview of what dynamic studies are. Any questions? Okay, next then, we want to take a look at what are called in vivo, but non-imaging studies. In vivo implies that we put a drug into the body, but non-imaging states very clearly, we're not taking a picture. We're counting something. We're counting a body part, the thyroid. We're counting a body fluid, urine, blood, plasma, something like that. So these are non-imaging studies. Now, in some cases, like a thyroid uptake test, you might couple it with a scan. If it's an uptake and scan, the uptake is in vivo non-imaging, and the scan, of course, is imaging. But if it's just a thyroid uptake test, it's going to be an in vivo non-imaging. Now, these two are not performed at all anymore. We can't obtain iron as a medical isotope. This one is rarely performed for glucose intolerance testing. Ocular P32, this was used to find ocular melanoma. I have never seen this study performed ever. It's in the books. Never have seen it in 40 years. Platelet survival. We used to do a few of these. Probably we've done 10 of them in the last 30 years, but none recently. And we're trying to determine why people's platelets are disappearing so rapidly. And this quantifies that disappearance rate. The really important one is this one. An RAIU. On your exam, you're going to see it worded as an RAIU, and you better know that that's a radioactive iodine uptake test. I put a star here for iodine instead of a number, because we can do this with I-131 or I-123. The uptake is sometimes done with I-131 if you're dealing with a cancer patient. And we're looking, of course, for abnormal uptake, too low, hypo, too high, hyper. And we're going to be counting the patient at time 0 and at time 24 hours and determining that percent uptake. Schilling test, I'm not even going to talk about it. It has been gone for many, many years. Red cell survival, splenic sequestration study. Almost nobody is doing chromium. It's very hard or impossible to get it now. But we used to do red cell survival and splenic sequestration as in vivo but non-imaging. We never imaged the patient. We counted blood samples and made those determinations. Okay, now we have covered the basic principles of radiopharmacy, and we're going to make a small dent right now in the big chart. Our residents at Loyola started fondly calling this the big chart because it's many pages in your notebook, and it is in fact a huge chart that lists every single drug that's sold in the United States, what it's used for, what's a prescribed dose, not my hospital dose, but the typical prescribed dose nationally. In some cases, some information about radiation dosimetry and so on. Now, there used to be some investigational drugs in the chart, but there aren't any anymore, so you can ignore the bottom line. But anytime in this chart that you see the name of a drug that is underlined, that is the agent of choice, the agent of choice nationally. So you'll see agent of choice underlined where there's a choice to make, almost always. So we're going to be looking at radiopharmaceuticals, typically prescribed doses, and the procedures that they're used for. Now, before we do that, I want to give you some guidelines that I prepared for you that will help you to remember what the prescribed doses are. It's very hard. We have a lot of drugs. We have, I don't know, 20 drugs, maybe more. Everyone has different doses, and there are actually different doses for one drug for different procedures. So it's an awful lot to remember. And so these guidelines are going to help you. If you just can't remember, they will help you a lot. So let's take a look. First thing is indium-111. We have several indium-111 compounds. There are no exceptions to this rule. If you are imaging a tumor, let's say indium-111 Octria scan, you're imaging a tumor, it's going to be 5 millicuries, whether it's a malignant tumor or not. If it's tumor imaging, 5 millicuries. Every other indication is 0.5. For example, indium GTPA for a intrathecal injection, 0.5. You're not looking for a tumor. Indium labeled leukocytes, looking for a chronic abscess. You're not looking for a tumor. Any other indication other than tumor will be 0.5. So that's a good rule to remember. No exceptions, 5 and 0.5. Secondly, for gallium, this is less important. We don't use it too often anymore. But for gallium, for all indications, it's going to be 5 to 10. People use more gallium for certain things and less for others, but it'll always be in the range of 5 to 10. For thallium, and again, we don't use this too much anymore, but for all indications, there is a maximum limit of 5 millicuries. And here's where that limit came into play. Back in the day when we were using cardiac, thallium for cardiac imaging with both stress and rest, we would do a 3 millicurie stress dose and then let the patient cool off for a few hours. And then we would give a 2 millicurie booster dose and perform the resting study. That was a maximum of 5 millicuries. Now, 5 millicuries doesn't sound like a lot compared to technetium doses that we use, but here's why there's a 5 millicurie maximum limit. For men, the testicular dose from 5 millicuries is 15,000 milligrams. That's a huge dose, a gonadal dose for a diagnostic scan. And so that limited it for men to 5 millicuries, and then it limited to everybody for 5 millicuries because for both men and women, the kidney dose was 5,000 milligrams. So that has always been the limit, 5 millicuries in one total procedure over 1 or 2 days. And that's where the limit came from. Now, for technetium, here are some guidelines. And, as you first look at these, it might sound very general, but they're going to give you a good sense of when to use a high dose. Let's define that as, let's say, 25 millicuries, or a low dose, let's say less than 5. So when do we give a high dose of technetium? So here are some of the reasons. Number one, the distribution volume is large. How large is your blood pool? If you are a 70 kilogram person, your blood pool is probably 5 liters. I'm probably closer to an 80 kilogram person, so my blood pool is probably 5.5 liters. That's a pretty big volume. And when you're looking at the heart, let's say you're doing a MUGA and you're watching the heartbeat and you're drawing a region of interest around a diastolic heart, what is the volume of blood in the heart compared to the blood pool? The volume of a diastolic heart is probably maybe 100 to 120 milliliters compared to 5 liters. You're looking at only a 2% volume in the heart in any given moment. 98% is not in the heart. And that's why you need such a huge amount to perform a MUGA, because The blood pool is huge in the body, but only 2% of it is in your field of view. So you need a really large number, like 25 millicuries. Or how about your bones? Distribution of bones is all over the body. And not only is it a very large distribution, but look at the next point. We send the patient away after the injection. Go away, come back in half of a half-life, 3 hours. We just lost 30% of our count rate waiting for the patient to come back. So we're always going to need a large amount for a bone scan for these two reasons: the delay and the very wide distribution body all over the body. And on top of that, what we're going to learn is that only half of the bone agent goes to bone. The other half either clears through the urine mostly, or a little bit of it hangs up in soft tissue. So we need big numbers for a bone scan for all of those reasons. Also, what if your organ uptake is suboptimal? I'll give you some examples of that. We're talking about 5% or less. That's suboptimal. Bone marrow imaging, that's not even important. We almost never do it, but let's look at a couple of others that are important. Myocardial perfusion uptake with Cardiolite and MyoView, 1.5 to 1.6% uptake in the myocardial muscle. What does that mean? 98.5% is in the wrong place. That's why when we give cardiac studies, some people give as much as 35 millicuries for the stress and maybe 20 or 25 for the resting study. So we need big numbers here because suboptimal. Also, what about symptomammography, where we're using Cardiolite to look for breast tumors in women who are typically at high risk, who have equivocal mammograms where we're not sure. That's a good indication for symptomammography. And what happens here? We're lucky if we get a 1.5% uptake in that breast tumor, and the rest of it is elsewhere. So anytime you have a poor uptake for any of those kinds of studies, you need a big number, like 25 millicuries. And here's some more reasons. What if the organ clearance is very rapid? For example, let's go back to that the rubidium I was talking about in the beginning. What do we say about rubidium? It's not that the organ clearance is rapid. It's only rapid because it's decaying so fast, so that in 5 minutes, you've gone through 5 or 6 minutes, you've gone through 4 or 5 half-lives. And so you need a big dose of rubidium. How much do we say we're giving? 40. Typical dose, 40. Could be 30 to 60, but huge dose. Also, if you're going to do SPECT imaging, you're going to need a bigger dose than planar imaging, because as your camera rotates around at all the different stops, you're at each stop for only 30 to 40 or 50 seconds. And so to get higher resolution scan, you need a little bit more activity. And finally, if the radiation dose is very low, you give a lot because you can without harming the patient. Think about a xenon ventilation study where we often give 20 or 30 millicuries. Why is that? Number one, rapid organ clearance, and the radiation dose is low because in 3 or 4 minutes, it's all decaying somewhere else, mostly in a xenon trap. Those are all good reasons for giving a high dose. And here are reasons for giving a low dose. And the perfect example is a pulmonary perfusion scan with MAA. Let's take a look. Distribution volume is small. The lungs are nice and compact. They're not scattered all over the body. Number two, how long do we wait? Patient inhales. I'm sorry, this is perfusion, not inhalation. How long do we wait though? We give the MAA and we wait 0, maybe 10 seconds, and because almost all of it is in the lungs in 15 seconds. It goes from antecubital vein to the right heart to the lungs, and it can't get past the capillary bed in the lungs. This is called capillary blockade. That's the mechanism's name. And so we don't need to wait more than 10 or 15 seconds, and we image. And because that lung uptake is quantitative, 95+% is in the lungs immediately, no delay. We only need 2 or 3 or 4 millicuries. The recommended dose is 2 to 4 millicuries in the package insert. We have been using 3 millicuries for the last 40-something years, there is no reason to increase that dose. And typically, we're doing planar imaging. Those are all reasons for giving a small dose. Okay, we still have about 10 or 12 minutes. And I think we're just going to dive in and let's cover the first few topics. It'll give you a sense of what's coming down the road for all of these radiopharmaceuticals. By the way, this chart is in alphabetical order of what we are trying to image. So it's going to be like abscess and bone and cardiac. It's going to be in that kind of an order. Now, the first thing is abscesses. And gallium, I want to show you a timeline, and then we'll come back to this slide. Gallium was used from 1965 to about 1970 as an investigational new drug. And people discovered that it was very good for finding both malignant tumors of all kinds, as well as abscesses and inflammatory sites. The Food and Drug Administration approved it in 1971. So now that's 50 years ago. We've had 50 years of approved clinical use of gallium. And then in 1976, that's 45 years ago, indium white cells, where we learned that we could take indium oxine, bind it to white cells, and we could find abscesses and inflammatory sites, not malignant tumors, but abscesses. And then 10 years after that, so that's 35 years ago, we have technetium labeled white cells that we label with Ceratec, which is HMPAO. So you can see there's a very, very long history, really 55 years of imaging for abscesses and inflammatory sites. Now let's go back. The one that I have underlined is technetium leukocytes. This is used more often than these other two put together. And for technetium leukocytes, we want to give 20 millicuries. Now, it's a little bit difficult to control the labeling efficiency for individual patients. So we take enough blood to get enough leukocytes that we should be able to prepare 20, 30, 40 millicuries. And usually if we get 20 or 25, that's what we inject. We never want to go below 10 millicuries. So indium leukocytes, this is used for chronic abscesses. This is a use for acute abscesses. And this is following that indium rule. It's indium leukocytes. It's not looking for tumors, a half of a millicurie. And this is following the rule here, gallium, 5 to 10. Now, to show you what a technetium white cell scan looks like, this is a teenager who has a retrocecal appendicitis. It's growing back toward the back of the intestines. And this is a study that was done on this young man. And take a look here. This is the inferior border of the liver. Because leukocytes go there and to the spleen. This is the infected area right here, this sort of a linear pattern. That's the appendicitis, urinary bladder. We're seeing some activity in the large vessels. It is a blood pool agent of sorts, white cells. And so this is very diagnostic of appendicitis. So why is this never used in the emergency room? And so we're going to ask that question right here. Number one, considering that the sensitivity and specificity of technetium leukocytes are both around 90%, why isn't this the procedure of choice in the emergency room rather than CT scan? Anybody? So let me give you a couple of reasons. Number one, the CT scan is very good at finding appendicitis. And number two, a CT scan takes 10 minutes. Think about what has to happen for indium to make our technetium leukocytes. We have to take 60 millicuries of anticoagulated blood from the patient. The central pharmacy has to come and pick it up. They have to drive back to the pharmacy. They have a 1.5 or 2 hour prep. They have to drive it back to you, and then you have to inject it, and then you have to wait 1.5 or 2 hours to take pictures. You're looking at a 5-hour procedure. Nobody wants to wait that long when someone's in the ER with a possible appendicitis that might be bursting. And so CT is, of course, the agent of choice. So would this work? Yes. Would anybody today do it? Definitely, definitely not. Question number 2. When looking for an abdominal abscess, what patient prep is required for gallium, but not for leukocytes? Anybody?
Citrus nitrate?
Yes. Did you say citrate? Is that what you said?
Citrus, yeah, citrate.
Yes. Yes. Okay. So yes, that's the correct answer is that we have to get the patients to do a bowel prep because unfortunately, gallium binds the fecal contents in the colon. We don't know why, but you don't want to call that hot stool sample a tumor or an abscess when you know what it is. It's just not. And so leukocytes do not bind to fecal contents. We wouldn't get a false positive. And so we prefer leukocytes for that reason, number 1. And number 2, patients have to do that bowel prep and they very unpleasant. If you've ever done one, I can tell you, they're not at all fun. So we would prefer leukocytes diagnostically and also because there's no bowel prep involved. When would you choose indium leukocytes over technetium leukocytes? And I'm going to combine that question with number 4 because the answer is all integrated together. What is the comparative in vivo stability of these 2 drugs? So when would we choose indium leukocytes over tech leukocytes? So if we answer the second question first, technetium leukocytes break apart in the body within a couple of hours after injection. Therefore, they are no good for looking for chronic abscesses where the uptake might not even appear for hours or even the next day. In that case, we would want indium leukocytes. We also want indium leukocytes because this has a 3-day half-life, 67 hours. And we can go out for 1 or 2 or 3 days if we need to. You couldn't do that with technetium anyway, even if tech leukocytes were stable, but they are not. They're very unstable. So you inject them, you wait, I'm not quite sure how long, an hour and a half, something like that. And you do your imaging and you're done because by the time you're finished, a lot of pertecnetate has appeared and it's all over the place. Okay, let's see, we have time for one more topic, and that is going to be another A topic, adrenal. And adrenal imaging today, if I were to underline one, it should be this first one. Almost everybody uses I-123, MIBG. It's meta, iodobenzoguanidine. If you ever studied chemistry, ortho, meta, and para are relative positions on a benzene ring. And this is the meta position. So it's got an iodine hooked to a benzene ring, and the benzene is part of the guanidine molecule. All right, that's more chemistry than you need to know. But the typical injected dose, we've always injected 10. Some people inject a little bit less. If it's I-131 MIBG, because of the very high radiation dose to the adrenal glands, we only inject 0.5 millicurie. Octreoscan, this is looking for any of these neuroendocrine tumors on the bottom here. Both of these drugs, MIBG and Octreoscan, can find any of these. But this is again following the rule. Octreoscan, you're looking for a tumor, 5 millicuries, it's indium. And this is very new. If you don't have a germanium gallium generator, there's no way for you to use dotatate, but no easy way. But this drug also localizes in all these tumors. So I want to clarify one thing, and it's going to take this slide and the next one to do so. MIBG is good for all of these tumors, and so is Octreoscan. But on the next slide, you're going to see a lot more tumors imageable with Octreoscan, but not with MIBG. So MIBG is only these neuroendocrine tumors, and then the Octreoscan binds to any tumor that has a somatostatin receptor site. And there are lots of those. I don't know if I have a listing. Yeah, here are some of them. Insulinomas, gastrinomas. These are tumors that secrete insulin and mess up people's blood sugar levels. Gastrin is produced, glucagon, they're hormones. islet cell carcinoma of the pancreas, pituitary tumors. So all of those are imageable only with Octreus scan. And these neuroendocrine tumors up here are imageable with both of the drugs. Now I want to show you, this is bad for the patient, but a spectacular scan showing at a conference. This is a lady at the age of 52. She had a solitary pheochromocytoma. They usually occur right near the kidneys, like here's a large one right here, but she only had one of them at the time. The surgeon removed it. She was fine for 8 years. Then all of her symptoms came back. Terrible headaches. It took her to the ER, and she had facial flushing and hypertensive crises and things like that. The surgeon had her on the OR schedule, and this was, gosh, 20 years ago when we first started using MIBG, and he had just heard about it. He said, you know, I know this lady has a pheo. I can find it on the CT scan. Here's the tumor that they found on CT. He said, but how do I know she doesn't have another one that I can't find? So he ordered this CT scan, and he could not believe his eyes. There are over, if you count every little ditzel here, every little tumor, there are 50 tumors in this patient. CT found this one and missed all the others. You might be thinking, how is that possible? CT can find 2 millimeter pulmonary nodules. How did it miss all of those tumors? And here is the beauty of molecular imaging. Every one of those white spots is a lymph node that has disease in it. And unfortunately, the lymph node did not change size and shape. When the radiologist looked at the CT scan, he said, oh yeah, I see this big tumor right here. But the rest of those, they're just lymph nodes. They had not enlarged at that point in time. And when they took one look at this scan, they took her off the OR schedule. You can't cut somebody open and take out 50 tumors, not possible. So they sent her home with alpha blockers and beta blockers, and just wished her good luck, because there's really no cure for this. Now, these pheos are they're really not malignant most of the time, but they're dangerous to the patient because their blood pressure is just, excuse me, it's just uncontrollable. Now, this will show you a dotatate scan, which is spectacular. It's a very good choice. If you can get the gallium dotatate, it's a very good choice. This is the same patient here, not the one we just saw, but a more current patient. This is an Octreus scan patient. And yes, they would have called it positive. There's something going on here and something going on here. But look what the dotatate scan showed up. There's tumors all over the place, in the skull, in the neck, the mediastinal area, and the abdominal area. Tumors just everywhere. This is an anterior view and a posterior view. Same here. So this Octreus scan, while it made a positive diagnosis, missed most of what's really going on. So dotatate, I think, is going to become the agent of choice for neuroendocrine tumors. It just has to become more available. Not every pharmacy has a gallium germanium generator. And dotatate, I put some information. I'm not going to read this to you. It's too much, but it's in your lecture notes if you want to take the time to read it. And just one or two more quick questions, and we'll be at a good stopping point. When we are doing a scan that uses I-123 or I-131, such as I-123 MIBG, we have to block the thyroid, and we block it with a drug called SSKI. It is a saturated solution of Ki, that's potassium iodide. We give it prophylactically. We give it, let's say, an hour before the injection, and then the patient takes it for the next 2 or 3 days if it's I-123, or out to 8 or 10 days if it's I-131. The only criterion is this: if it's bound to a benzene ring, you should be blocking the thyroid. How about this though? What would happen if you gave somebody a big load of potassium iodide, 100 milligrams of potassium iodide, and then try to do an RAIU, a thyroid uptake test, what is going to be your percent uptake?
It would be none, right?
It would be 0, none. You won't get uptake. You gave 1,000-fold excess of what it takes to block the thyroid gland. 100 milligrams of this will block the thyroid of an elephant for a week, maybe longer. And so there will be no uptake of radioactivity at all. So here are the answers to how long do you block? Iodine-131 bound to a benzene ring, 8 to 10 days. I-123 bound to a benzene ring, 3 days. And for a thyroid uptake, you would never block for a thyroid uptake. Okay, how would you match these up? Both of these drugs are good for all 5 indications, but MIBG is better for 3 of them, and Octreoscan is better for 2 of them. And here is what most doctors would agree about, that anything here ending in an OMA is a solid tumor, and MIBG is preferable. And for more diffuse kinds of tumors like carcinoid and medullary carcinoma of the thyroid, Octreoscan would be better. Okay, just a couple of more questions and then we truly will be done. Which confers a higher radiation dose to the adrenals? 0.5 millicurie of I-131 or 10 millicuries of I-123. The radiation dose for I-131 for equal activities is a ratio of 70 to 1. So this 0.5 millicurie is a much higher adrenal dose than even 10 millicuries. That's 20 times as much of I-123. Higher image quality, definitely I-123, which permits imaging out to 5 days, definitely I-131. Which of the following drugs interferes with MIBG? Labetalol, excuse me. Labetalol is the beta blocker that interferes. Cocaine, heroin, morphine, all those kinds of drugs. Advil does not. Metoprolol does not. It's another beta blocker, but it does not interfere. Can we give MIBG to a baby? Yes, I've injected babies a week old looking for neuroblastoma. Pediatric dose. Why would we give a big dose like 5 millicuries when an adult gives 10? The reason is we have to image out the 40 hours. That's 3 half-lives. That's 1/8 remaining. That means that 90% is already decayed, aside from what cleared. What if you were asked this question on your board exam? You went to prophylactically block the thyroid with iodine, but the patient says, hold on, I'm allergic to iodine. How do I know you're not going to harm me with the drug? Now, you've been warned. And so if you gave iodine and that patient had an adverse reaction, that would be pretty much medical malpractice. So there is another drug. It's potassium perchlorate. And finally, there is a role for MIBG or indium-111, the Octreoscan therapy. It doesn't work most of the time. On a rare occasion, this is a spectacular cure, but mostly it's a waste of time, money, and radiation dose. I'm going to skip that one. And we're going to start here next week. I'm going to stop the screen sharing for a moment so I can see all your pretty and handsome faces here. And I'll just see if you have any questions about anything we have covered today. I know it's a lot of material. I tell classes sometimes it feels like you're drinking from a fire hose. It's just coming so fast. But you've got your lecture notes there. You should have them in electronic format. Also, if you will look in the chat room, I put a small PowerPoint file there for you. And that file is the slides that I prepared for you yesterday on the rubidium generator. So if you want to download that file and save it on your computer, you're welcome to do so. It is now an integral part of the notes and I'm going to keep it there permanently. So any last minute questions from anyone? Okay. Okay, if not, again, thank you for your attention and I will see you next Thursday at 9 a.m. Have a good week.
Thank you.
Thank you.
Thank you.
Bye.
Very welcome. Bye-bye.